Okay, so as in the case of the linear momentum, we're going to deal with the infinitesimal rotations first, and then see how we can go from the infinitesimal rotation to finite rotations by going from just a couple of terms to the entire exponent itself. All right. So we are going to write the change in x for an infinitesimal rotation, and we already did that last time, and we saw that basically an infinitesimal rotation can be written as 1 plus epsilon. 1 is the identity matrix in here. This is something in SO3, so it's a special orthogonal matrix. Of course, the full thing involves higher order powers than epsilon, but if we just keep the first one in here, then the orthogonality requirement means that R times R transpose is equal to the identity matrix, which means that 1 plus epsilon times 1 plus epsilon transpose is equal to the identity matrix, which means that 1 plus epsilon transpose plus epsilon transpose is equal to 1. Now the whole thing is orthogonal, but epsilon itself is not orthogonal, so epsilon times epsilon transpose is not equal to 1, but it's of the second order in epsilon, and so if we retain only first order expansions, then we have this. 1 plus epsilon transpose is equal to 1. The 1 cancels out on both sides. That means epsilon plus epsilon transpose is equal to 0. That means epsilon transpose must be equal to minus epsilon. That means epsilon necessarily an antisymmetric matrix. Okay? And all the epsilons are real. And those being an antisymmetric matrix, a 3 by 3 antisymmetric matrix, as we saw, has 3 independent components. And those 3 numbers would in some way describe the particular rotation that you are talking about. Okay? All right. So the epsilon matrix looks like this. Being antisymmetric, then all diagonal elements has to be equal to 0. And so there's this epsilon 1, 2, epsilon 1, 3, epsilon 2, 3. Being antisymmetric, this is 2, 1 must be equal to minus 1, 2. So this is the minus of that. This is the minus of that. Minus 1, 3. This is a minus of that, and so on and so forth. So there are only these 3 independent numbers for a particular infinitesimal rotation. Okay? So we're going to say that's epsilon. And we know that last time we saw that the change in the coordinates of a particular point in 3-dimensional space induced by an infinitesimal rotation is just epsilon ij xj. This is a small rotation. Okay? Where again the j is summed over, so a particular change in a particular component, a rotation change in one of the components would depend on all the other components also in general. Okay? But there are only 3 independent terms in here because there are only 3 independent numbers, epsilon, in here. Okay? So we'll start with that expression. Bearing in mind now the very important property that epsilon is an antisymmetric matrix. So epsilon transpose is equal to minus epsilon, like that. So now we're going to require the scalar transformation property that psi prime is equal to some unitary transformation which would now depend on the 3 values of the epsilons. So I'm going to write it like that, operating on the original wave function. Okay? And now, again, it's the same coordinates. Okay? But this is equal to, if I call the rotation A, so which is written as 1 plus epsilon, right? Just as we had a minus sign over here, psi prime in the translational case is equal to psi prime at x is equal to psi at x minus the translated amount. So we're going to write psi prime at x is equal to psi at the inverse transformation of x, like that. Okay? So this is the analog of x minus epsilon. It's the inverse rotation, okay? Acting on the original coordinates x in here, okay? But this being orthogonal, so I can replace the inverse by transpose in here, like so, okay? And so this is psi at the value 1 plus epsilon transpose operating on x. And this is like psi. Now these are matrices, right? This is a 3 by 3. This is a 3 by 3 also. This is x is like a column matrix. And this is something like x1, x2, x3. You see what we are doing over here? I'm just writing x to stand for the collective coordinates in here. Okay? So this is like a 3 by 3 operating on this column matrix, which produces another column matrix, and so on and so forth. Okay? So obviously, you can write this psi at... Now, epsilon transpose is equal to minus epsilon. So this is 1 minus the matrix epsilon operating on x. Is that okay? All right? Step by step. There's no ambiguity in here. So this is equal to psi at x minus epsilon x. And again, at this point, we can do a Taylor's expansion. Okay? And we are going to get... I'm going to write back the dependence on all the different coordinates. Psi at the original value of x minus... Now, Ex is a matrix, okay, which is a column matrix. Ex, the ith component in here, multiplied by x, let me see. Yeah. Ex. So, okay, here's what we do. Exi, okay, this is a little change in it, ith component of the change. And the Taylor's expansion, the first term involves taking the first derivative of psi like that. So this step is Taylor's expansion. Okay, plus higher order terms, which we're going to ignore because we're just dealing with an infinitesimal rotation at this point. Okay? All right. Moving on. So this is equal to psi at xi. Now this is a product matrix, right? What is the I component of the product matrix? It must be equal to epsilon I j xj, but j is summed over. Okay? The product of epsilon and x as matrices, and then di psi, like so. Plus higher order terms, starting with epsilon squared, which we're going to ignore. Does everybody see this step in here, which is important? Okay? Again, neither side has any free-floating indices, right? Psi itself is a scalar function, so it doesn't have any free-floating index, although it depends on the three coordinates. Here, both I and j are summed over, so it doesn't have any free-floating index, and so on. Okay? And now, let us look at this term in here. That's the second term in here. This is the one that is of importance, so let's look at it. Epsilon I j di psi. And I'm going to write this as sticking in the h bar, okay? I'm going to write this as I epsilon sticking to the p rather. So I'm going to replace the ddi by p, and I'm going to write it like this. I'm missing something in it. There's an xj in here. Right? There's an xj in here. So it's I epsilon I j xj pi psi. Okay, the DDI gets represented by minus IH bar. IH bar P, like that. Okay. Well, again with H bar, I think this is it. This is it in here. Okay. Okay. Now you see I is summed over, J is summed over, but then when you sum over I and J in here, there are only 3 independent numbers. Well, there's 6 possibilities actually. I cannot be equal to J, right? When I is equal to J, the epsilon is equal to 0. So it's either I12, epsilon 12, epsilon 21, and epsilon 13, epsilon 31, and epsilon 23, epsilon 32. But one of them is a negative of the other, okay? Because the epsilon matrix is anti-symmetric. And so when you put in the summations explicitly, you are going to get, write the expression in terms of the 3 independent epsilon numbers, epsilon 1, 2, epsilon 3, 1, and epsilon 2, 3. You're going to get something like this, x1 p2 minus x2 p1 plus I epsilon 3, 1, x3 p1 minus x1 p3. And go home and verify this, okay? And of course this is operating on psi plus I epsilon 2, 3, x2 p3 minus x3 p2 operating on psi. And these are precisely the what? The 3 components of the angular momentum, okay? Because angular momentum is R cross P, okay? Because of the rules of the cross product. And now, let me just go ahead and define x1 p2 minus x2 p1. I'm going to define this to be the 3rd component of the, because there are 3 independent ones in here, corresponding to the fact that there are 3 independent numbers for 3-dimensional rotations. So I'm going to define x3, 1. I'm going to define this as L2, 2nd component of the angular momentum. And clearly this is going to be defined as the 1st component of the angular momentum, like that. Okay? And I think that just about does it for us. And so the now these 3 numbers, okay, collectively can be thought of as the 3 components of this vector in here. All right. And so it's then like the scalar product. This is apparently the 1st component. The 3rd component of this vector, and that one is attached with L3. So this is like the 2nd component. Epsilon 3, 1 is the 2nd component of that vector. Epsilon 2, 3 is the 1st component. So it's like the dot product of these 2 vectors in here, like that. So you can write it like that. Okay? And you see there's a minus sign in here, and this is important. This minus sign gets retained over here, like so. Okay? So there's always e to the minus something like so. So these are the 2 sort of important relationships for the unitary operators corresponding to linear momentum and angular momentum. Now let me mention one fact, and this has to do with a special situation that we are dealing with 3-dimensional rotations. The very fact that we can associate these 3 numbers, the epsilon, the 3 independent epsilon numbers as the components of a vector is due to an accident that we are dealing with 3x3 matrices. Because a 3x3 antisymmetric matrix has 3 independent components, okay? But if we happen to be dealing with 4-dimensional rotations, then we are left with a 4x4 antisymmetric matrix, okay? How many independent components does a 4x4 antisymmetric matrix have? 6. That's not equal to 4. So those 6 things cannot be thought of as the components of a 4-dimensional vector, okay? So that's not quite correct. I mean, we can only associate, that's why these things, these three-dimensional vectors, such as angular momentum, are called pseudo-vectors. They don't really transform like vectors. They're actually rank 2 tensors. They're rank 2 tensors because there are 2 independent indices associated with it. Okay? It's more properly to think of this as the 1-2 component of a certain rank 2 tensor. Okay? And then the 3-1 component, and then the 2-3 component. This is an important point which is usually glossed over in introductory physics classes because we only usually deal with 3-dimensional rotations. But when you come to special relativity, right there, you're dealing with 4-dimensional rotations. And then, of course, there, you don't talk about rotations in because of a different metric in the Minkowski space. The rotations are not just SO rotations, they become the Lorentz transformations instead. Okay, but you do have to be careful about this tensor business so that the angular momentum is not a real vector, so to speak. Rather, it is more properly thought of as a rank 2 tensor. Okay. Now, let me go back to talk about this rotations in 3 dimensions. Now, any rotation in 3 dimensions is an element in the SO3 group. Okay, so any rotation is an SO3 matrix, which means any rotation is an orthogonal 3x3 matrix whose determinant is equal to +1. Different matrices represent different rotations. Okay, and so on and so forth. Now, each rotation in 3-dimensional space depends on 3 parameters, independent parameters. Again, you can look at these as the independent parameters. They can assume continuous values. Okay? There's no limitation on those values, so to speak, at least within a certain manifold. So you can think of each rotation as living in a manifold of dimension 3. And you can even think of it as having a certain shape. Okay? So that is why we say that the SO3 is a continuous group. That means each set of parameters describing a particular rotation can assume a continuous range of numbers. There's a certain range to them. Okay? So the angles, for example, have a certain range to them, and so on and so forth. Now, what is a convenient way to think of the shape of this manifold? Okay? One way is like this. Now, I have already said that a particular rotation can be thought of as a rotation in about a certain direction through a certain angle. And let's say you talk about rotation in 3-dimensional space, which I'm going to characterize like this. And let's say that this is a particular vector which describes the rotation, and the rotational angle about this axis is theta. Then the vector has length theta, and its direction is along the direction of the axis of rotation. And rotation by a positive angle is always it's the usual choice. Is thought of as having the right-handed sense. That means that if you're rotating about this axis by a positive angle, then you go this way. If it's a negative angle, then you still use your right hand and go that way. It's always right-handed. Either you choose a left-handed or you choose a right-handed. You never mix the two. If you mix the two, then it becomes totally confusing. Okay? So you have to be careful. Most of us are right-handed people. That's why by convention we always use right-handed coordinate systems and not left-handed coordinate systems, and so on and so forth. So you have to be careful about that. Okay? Now, possible directions are all over the place. So you can think of the directional space as being a unit circle, since this is a unit vector, right? This vector can assume all sorts of directions in space. So the possible directions is just like the face of a 2-dimensional sphere. Okay? So each point on this unit sphere, that means a sphere of radius 1, represents a possible, each point on the surface in here represents a possible direction for the axis of rotation. And so already there are infinitely many possible directions. But then that's not the only thing giving information about the particular rotation. You also have to tell what the finite size of the rotated angle is. Okay? And so then, as we did before, you would characterize a particular rotation about this direction by drawing a vector whose length is the size of the rotational angle times this unit vector like this. Okay? Now just think about it a little bit. What are the possible values of theta? About a certain direction, how much can you rotate? 0, you would think that is 0 to 2 pi. But there's a little complication in here which is very, very interesting. Actually, you only need to go from 0 to pi because of this fact that I'm asking you to prove that a rotation about n by angle theta is equal to, it's the same rotation physically as a rotation about minus n by 2 pi minus theta, both in a positive sense, in a right-handed sense. Think about this a little bit. This is one of the problems I asked you to prove. Okay? So you actually don't need to go from 0 to 2 pi. You just need to go from 0 to pi. The rotation angles that are bigger than pi can be represented by some rotation about the axis minus n instead. So it's on the opposite side. So you draw a vector that's like this. Okay? A rotation by theta about this axis is equal to a rotation in a right-handed sense about this direction by an angle 2 pi minus theta. Okay? All right. Now, something interesting about the value pi. Because of this situation, a rotation about n by pi is exactly the same as a rotation about minus n by 2 pi minus pi is pi. Okay? So rotation about any direction by pi is exactly the same as a rotation about the antipodal direction by the same angle pi. Okay? So in order to specify all the possible rotations, I can take a sphere of radius pi. I can draw a sphere of radius pi. So this radius is pi in here. Actually, any point inside the sphere would represent a unique and distinct rotation. For example, a point here inside a sphere, which means that the rotation angle is less than pi, right? Because the entire radius is pi. So this point inside the sphere would represent a rotation about this direction by an angle, whatever the length of that is, which is less than pi. Okay? How about the identity rotation? How about a rotation which does not rotate at all? Where is that going to be? Which would be the center of the circle. That's the identity rotation. Any other point is not the identity rotation. But something interesting comes along. You would think that, okay, so then the so-called differentiable manifold, which is the manifold of the particular Lie group SO3, is the sphere, right? But you would be wrong in a very important way, because of the fact that in an ordinary sphere, this point is a completely different point from the antipodal point. They are two different points. I'm here in LA. I'm not sure where the antipodal point is. Someplace in China. Those are two different points. Okay? But here, a rotation by pi, which is this point, is exactly the same rotation about minus n by pi. So this point is taken to be the same point as that point. It's as if you live in a world where LA is the same place as some place in China. And you can write, a science fic based on that particular description. Okay? So you try to think of the shape of the group manifold. It's a three-dimensional differentiable manifold, but it's not a ball because a ball has antipodal points distinct. Okay, this is a very special kind of a ball where only the internal points are distinct, but the external points but the points on the surface of the ball have to be such that the antipodal points are considered as identified, meaning the same point. Okay, it's kind of like if you take a line segment, the beginning and the beginning and end points are different, but if you change this a little bit and curl this line segment up so the two ends join each other, so the two ends join becomes the same point. It's a different topology from that one. So this guy in here, where the antipodal points are to be identified, is of a completely different topology from the topology of a solid ball in three-dimensional space. And this is one very important aspect of the group manifold, the so-called group manifold of the group SO3. It takes on this kind of funny character. It leads to very interesting, important facts concerning the group, 2-to-1, homomorphism and so on. I'll talk about that later, but for the time being, let me just ask you to keep this in mind, okay? Now, so all that I've been talking about is concerned with this special group SO3. All right. Mathematically, what is SO3? SO3 is mathematically the set of all 3x3 special real orthogonal matrices. Okay? So the things that live in here, each one of them is a 3x3 special orthogonal matrix. And how many are there? There are infinitely many, okay? Because there are infinitely many points in this manifold in here, okay? And so there's a geometry to this group in here. The geometry is described by the geometry of this, the geometry and topology. This is called the geometry and topology of the group manifold. These kinds of groups, the continuous groups, where the group parameters can be thought of as coordinates in a particular manifold, are called Lie groups. Okay, so Lie groups has continuous parameters. It is distinct from what is called discrete groups. Discrete groups consist of a set of elements which together form a group, and those elements can be counted. Okay, the elements in here cannot be counted. Discrete groups are countable sets. Okay, even though they may be infinite, they are countable. Lie groups has a group manifold associated with it, usually a differentiable manifold, and so it has a differentiable structure, and so on and so forth. Okay? It being a differentiable manifold, you can think of tangent spaces to that manifold. Tangent spaces are linear approximations of a particular neighborhood of a manifold. Okay? And linear approximations correspond to small changes in a certain neighborhood. And so these infinitesimal generators, such as the linear momentum or the angular momentum and so on and so forth, can be thought of as objects living on tangent spaces of this group manifold. Which tangent space? Because each point has a different tangent space. The linear algebra is, in fact, exactly the tangent space to the identity of the Lie group. Okay? So the Lie algebra is, that's why it's the Lie algebra. Things living in the linear algebra contains infinitesimal transformations, because infinitesimal transformations is kind of like, in the case of a linear one variable, you've got a function like that. If you want to investigate the behavior of this function in a certain neighborhood of this point, differential calculus tells you, you look at this tangent line in here. So we generalize the concept. Instead of, the tangent line at a certain point in a function of one variable, we look at a tangent space at a certain point of the manifold. Corresponding to each point is a different tangent space. It's a linear vector space. The dimension of that linear vector space is the same as the dimension of the manifold. Okay? So SO3 as a manifold is a three-dimensional manifold. So each tangent space at a different point of the manifold is a three-dimensional linear vector space. So it has a linear vector space structure. And so the linear algebra that is defined as the tangent space at the identity, because it tells you what happens when you are not too far from the identity, right? When you keep only the first order terms in those exponential expansions and so on. The linear algebra are then the tangent space at the identity. It's a three-dimensional linear vector space. And it being a three-dimensional linear vector space, you can choose three independent vectors as the basis vector. And so in this sense, you can choose L1, L2, L3 to be the basis vector of the tangent space at the identity. That tangent space at the identity is called the linear algebra corresponding to the Lie group. I'm sorry, it's called the Lie algebra corresponding to the Lie group. Okay? So there's these mathematical ways of describing Lie groups. Now, one more thing I'd like to say is that, what is called a fundamental representation, this is how the group is actually defined. Each object in the group is a 3 by 3 special real orthogonal matrix, right? But the point is then, all of a sudden you represent a particular rotation by this kind of strange piece in here. This thing is not a 3 by 3 matrix. Okay, it may be, okay, it may be, but this thing is not even real because this thing has an I in here, okay. And so these are called different representations of the group. This is a particular representation called a unitary representation of the group. And in the study of group theory, then it becomes very important to find all the different representations of the same group. A representation, I'll go into this in detail, can be viewed as a particular operator acting on some vector space. You see, what do these operators act on? Functions. You can think of those functions as things living in a vector space, right? What is that vector space called in quantum mechanics? Hilbert space. What is the dimension of some typical Hilbert space? Infinite. Okay? The dimension of a Hilbert space is infinite in general. All right? It's just that in general. A Hilbert space, you can talk about subspaces of a Hilbert space, which is finite. But, if you think of the space of all continuously differentiable functions, it's an infinite dimensional vector space. It can be viewed as a vector space because you can add functions to get another function which is in the same space, and you can multiply a function by some numbers and get another function in the same space. Okay? And so it has a linear structure to it. But when you ask what is the dimension of the space of all continuously differentiable functions, it is infinite. Okay? You don't even have to talk about ordinary, complete general functions like that. You talk about periodic functions. And you've already learned in Physics 308 that periodic functions can be expanded in terms of what kind of series? Fourier series. How many terms does a Fourier series have in general? Infinitely many terms. Each of the functions, the sine nx, where n is 1, 2, 3, and so on, a cosine nx, can be viewed as a particular basis vector. Okay? So there's a component which is the coefficient associated with sine x, and there's another coefficient associated with sine 2x, another coefficient associated with sine 3x. The collection of those coefficients defines the function for you. It's an infinite dimensional space in general, because Fourier series are in general infinite. Okay? And that's a Hilbert space. All right? A space of periodic functions can be viewed as a Hilbert space. It's infinite dimensional. It satisfies certain other mathematical properties also, which I'm not going to go into in detail again. This is not a functional analysis class. Okay? So what are we talking about in here? Let me just mention one more point first, and then I'll get to your question, Ian. We're talking about something that acts on an infinite dimensional vector space. Okay? So as such, this particular group element is represented by some infinite dimensional matrix. All right? obviously it's not the only representation. You can talk about it acting on subspaces also, okay, and so on and so forth. So we have to, whenever you talk about a group, whether it's a discrete group or a Lie group, you always worry about all the different possible kinds of representations. This thing that we have built up, the unitary operators acting on wave functions, is one very particular representation of the rotation group. Yes?
So I was going to mention that you can have finite dimensional
subspaces. Yeah, you can call them a Hilbert space, but in general, in the most general definition, a Hilbert space is a countable infinite dimensional space.
Can't you have uncountably infinite Hilbert spaces as well?
No, Hilbert spaces are usually countable. I think there's a special definition for that. Besides that, there's a couple other requirements also. Okay, so the periodic functions is countable because the basis vectors can be counted: sine x, sine 2x, sine 3x, cosine x, cosine 2x, cosine 3x, and so on and so forth. You can count those. Okay. Yeah. But in general, we are talking about infinite dimensional Hilbert spaces in quantum mechanics. So at this point, perhaps it would be useful and convenient to kind of go into the abstract aspect of group theory a little bit before we come back to study, in particular, this rotation group and so on and so forth. And this is how I wrote the book. So we kind of take a detour at this point and talk about general group theory. And so let me give the definition of a group in here. This is all spelled out in definition 4.1. You don't have to copy it down, but it's very simple to say. And it's amazing that, encompassed in this simple definition is the almost infinite rich content of group theory. Very diverse and interesting aspects, mathematical aspects of group theory and so on. So what is a group? A group is an algebraic category. That means it's a collection of entities with only one rule that combines the different entities, and that's usually called a multiplication rule within group theory. So a group G, let's say a group G, okay, is a set of elements, one typical one of which we usually write it as little g. So little g is an element in this group G. The set can be an infinite set or it can be a finite set. So there are groups obviously consisting of infinitely many elements, uncountable or countable, and there are groups consisting of finitely many elements. There's a group consisting of one element, and there's a group consisting of two elements, three elements, and so on and so forth. Okay, you can build up all sorts of examples. Yeah?
What is capital G?
It's the group itself. Little g is a particular element in a group. Okay, so that's how we write things. So we say that little g is an element in the group itself. Okay? Now, here are the group axioms, so to speak. It satisfies four conditions. Number one, now remember, a group is defined by an internal operation called multiplication, okay, which we usually call group multiplication. So the first property is that if you have two group elements, any two may be the same. Any two elements in a group. First property is called closure of multiplication. Then following the particular group multiplication, the product of these two elements is also in G. Okay, this is called closure in multiplication. Okay, and it's in general. I'll come back to your question. It's in general recognized that multiplication, group multiplication, is not commutative in general. Yeah.
Is it similar to the rules of vector spaces then?
No, the vector spaces you have more than one operation. You have the addition operation, and then you have this other operation called scalar multiplication. You can multiply a vector by a scalar and get another vector. There's no such thing in here. Okay. The group is like the simplest algebraic category, so to speak. Okay? It is only one internal operation called a multiplication. So this is the first rule. Number two, and that is It satisfies the usual multiplication rule called the associative property. So this one is closure. So if you have three elements, G1, G2, G3, and if I multiply G2 and G3 first together, you get another group element, which can then be multiplied with G1 to form, this would be another thing in the group, okay, because of the closure property. The associative property simply says this, that this is equal to G1, G2 bracketed, and then G3. You would think that this is, of course, obvious, but you know, it's taken as an axiom. There are things which don't satisfy this associative multiplicative axiom, and then such things are not called a group. Okay. Number 3, there's this thing called the identity element, which we usually write as E, so that given any group element G, GE is equal to EG is equal to G. This is called the existence of the identity element. Okay. 5, existence of an inverse. Given any group element G, there exists an inverse that we are going to write as G minus, such that G minus 1, such that G minus 1 multiplied by G is equal to the identity element. And given this, you can also show that C is also equal to G times G inverse in the other order. Okay? Identities have to satisfy these four axioms, and any set of objects satisfying with a given multiplication rule that satisfies these four axioms is called a group. So it's a very general kind of a thing. Now, if you take away the last axiom, the existence of the inverse, sometimes you have things which satisfy the first three but not the fourth. Okay? And this is called a semigroup. Semigroups are not used too much in physics. There are some places where it's used, but since it's not very often used, let's not concern ourselves too much with it. From now on, we'll just be talking about groups. Now, immediately, let's think in terms of the rotation group, right? So G is our old friend, SO3. Each SO3 is a special orthogonal matrix. You can prove that you take the product of any two SO3 matrices, the result is also SO3. The result is also an orthogonal matrix. This is very easily proved, and I encourage you to go home and prove it, although this is not listed as an exercise. If you have two matrices that are separately special orthogonal, then a product in either order is going to be an other special orthogonal matrix. Okay, so that satisfies SO3 matrices satisfy the first property, right? And you can also verify pretty easily the multiplication of any matrices satisfy this property, right? Well, only when you're talking about matrices of the same size, okay? Multiplication of matrices of the same size satisfy this so-called associative property. So SO3 also satisfies number 2. And finally, what is the identity in SO3? It's just the identity matrix, identity 3 by 3 matrix. Finally, given any rotation, you can undo it, so to speak. So given any rotation, there's always an inverse, such that this last axiom is true. So once you can prove those four things, then you can declare that the set of SO3 matrices is a group. Okay? All right, let's stop here. Let's pick up from here next time. Next time we'll come back and talk about the Lie algebra. Oh, we'll introduce the idea of a group representation. First, I've already mentioned that a little bit. And then we're going to come back to the Lie algebra of SO3. Okay?